All right, guys. So we're going to pick up where we left off in lecture yesterday, but this will be maybe tomorrow for you. Does that make sense? No, it doesn't make sense. Doesn't matter. Picking up with the power series stuff. This is a lot of just sort of the formalization of what we were talking about on Tuesday. So some of it is important, some of it isn't. I'll try to throw in some examples so that we can at least see how it all comes to pass or how it works. But we're just gonna do some theory. All right. So what we saw last time results in some theoretical consequences. So we've got a theorem here. What does this theorem says? It says, this theorem is the convergence theorem for power series. What did it say? It says, if we have a convergent power series, so this guy converges, and we say it converges for, or I guess at x equals c, which is something non-zero, then what can we say? Then we know that this power series converges absolutely. Converges absolutely for all x less than the absolute value of c. So if we know it converges for one particular x value that's non-zero, then we know it converges for any x less than the absolute value of c. Right? And I should have said absolute value of x less than the absolute value of c. Conversely, which means on the other hand, right? Conversely means on the other hand, if the series diverges at x equals d, d for divergence, right? Then our power series diverges for all x whose absolute value is greater than b. So this is a really complicated way of just restating the radius of convergence, or at least radius of absolute convergence, right? This is all about absolute convergence or divergence. There's a corollary, which is a fancy way of saying a consequence of the theorem. So a follow-up theorem, if you like. And what does that follow-up theorem say? It says, suppose we have a convergent power series centered at A. So this thing converges. Then one of three things happens. And this is pretty much the results that we discovered on Tuesday when we were just breaking it down for individual problems. So what does this corollary say? It says there exists, that's what that backwards E means. There exists some R, there is some R greater than zero, such that, ST, such that our power series diverges for any x minus a greater than r. So this is really all just a fancy and very compact way of saying what we just said up here, but for a power series that is centered at A instead of just at 0. So this R is equivalent to the D we see here. So we can say it's divergent for all those, and we can also say it's absolutely convergent for all the x's minus a's that are strictly less than r. There is a caveat, which we saw on Tuesday, which is our power series may or may not converge on the endpoints. And those would be x equals a plus r, or x equals a minus r. So just like we saw on Tuesday, we could have convergence on the endpoints. We have to check them individually, but we'll definitely have absolute convergence within the radius, strictly within the radius. All right. What else can we say? We can say our series converges absolutely. So these are all follow-ups. So this is one case. One case is we have some finite interval for which we have absolute convergence, and we may have convergence on the endpoints. One other possibility is that this thing converges absolutely for any real number. So this R means all real numbers. And we saw an example of that on Tuesday, right? So we could either have convergence on the interval, we can have convergence over all the numbers. And what was the third possibility? The third possibility was that it only converges at the center. It only converges there, and it diverges everywhere else. So for any x outside of A, which we can say very succinctly this way. Okay, so I like to use these symbols just so I don't have to write as many words, especially when I have such a small board. But what is it saying? The third possibility is saying we could only have convergence at the center and nowhere else. That's what it's saying. So the corollary is just recapping everything that we saw on Tuesday. Convergence on the interval, maybe on the endpoints, convergence for all real numbers, or convergence only at the center. So those are the three distinct possibilities. Haven't said anything new that we haven't already observed, but needed to say it formally. So that's all, the theorem of convergent power series. Okay. Few more theorems, and then maybe we can get to some examples. All right. Another theorem. What does this theorem say? So this theorem says, suppose I have a convergent power series centered at 0, and that this converges to a function capital A of x. And really, this is important. You know, it looks like it's just notation, but there's really an important theoretical thing happening here, which is saying that the power series is more than just the series, it's a function of x. And this is something that we saw on Tuesday. I called it, you know, turning the dial. That this really is a family of series, and we can turn the x dial to different values. And each time we choose a new value, we get potentially, or we get a new series. And for some values that we select, this thing can behave differently. Sometimes it will be absolutely convergent, sometimes only conditionally convergent, and then sometimes it'll be divergent. But if we think of it of the whole thing as converging, it converges to some function of x. So obviously this is only for the x's that are within the radius of convergence. All right, so we have one such power series, and suppose we have yet another power series, both of them centered at 0, and this one also converges to b of x. And what's important here is that we have absolute convergence for both of these series, both of these power series for any x less than some r value, right? So in general, the radius of convergence for two power series won't be the same. That's okay, because I could always just choose the smaller of the two. Since they're both centered at 0, so let's say the radius of convergence for the first one is between -2 and 2, and the radius of convergence for the second one is between -1 and 1, then I'll just choose r to be 1, positive 1. And then I know they both converge absolutely for that r. So if you want to get technical, you'd say the minimum radius of convergence will be whatever that r is. All right, so we have these assumptions, and we're going to say let the coefficients here be defined as follows. So the coefficients C are defined in terms of A and B. So think of the A coefficients are just walking up one by one, and the B coefficients are walking down one by one, right? So they'll sort of walk past each other, meet each other in the middle, and then go past each other. So I have a new set of coefficients here. Then if I define a new power series, Cn x to the n, then I can say that this power series will converge to the product of those two functions. It'll converge absolutely for all the x's less than r. So in practice, this isn't super useful. You don't see this coming up very often because it has very strict constraints. In particular, we need this to define it this way. But I mean, you know, it could come in handy if I can look at a power series and break it up into two different power series in some way, basically factorize it. Then I can, if I know the convergence of the two factors and I know the convergence of the whole thing. That's basically what it's trying to say. But like I said, this doesn't come up in practice very often. Just something worth seeing, worth talking about. All right, another theorem. This one is more useful. Doesn't have a name. But what does it say? It says we have a convergent power series centered at 0. And I say it converges to some function of x. That actually, this doesn't matter. reading my notes wrong. So this is convergent, it's absolutely convergent. All that matters is I know its radius of convergence. And so I have a convergent power series centered at 0, and I have a function that is continuous. So continuous function. Call it f. Then this theorem says that the sum of the ANs times the f of x's to the n converges absolutely as long as the function is within the radius of convergence. So that's a nifty one, because we could very well be looking at power series where we can think of the x term as being a function of x, and then maybe we can simplify the analysis. So here's an example. Let's say we have series x to the n, right? Sort of the normal geometric series, and we consider the series 4x squared to the n. Then 4x squared, we know that this is convergent. So let's do the analysis. We say, hey, this thing is convergent as long as x is strictly less than 1. Okay, so what does that imply? That implies that this other power series, 4x squared to the n, converges absolutely if the absolute value of 4x squared is less than 1. All right. What does that tell us about our x? That tells us that our x needs to be between, or the absolute value of our x needs to be less than 1/2, or we could say negative 1/2 is less than x, which is less than positive 1/2. So see how we use the radius of convergence for the series to help us, for the series without the function, to help us determine the radius of convergence for the series with the function. So that can be useful going forward. Maybe we can see a given series in this way, and it'll simplify how we approach the problem. Okay. All right, some substantially more useful theorems coming at you here. So now we can start seeing where power series shine, why they're important. All the other stuff is just sort of interesting consequences of looking at power series, but here we're gonna start laying the groundwork for what's gonna follow, which is some of the most useful material. So now we're gonna look at a power series centered at A. And we're gonna say that that thing converges to some function f of x. Of course, we know that it converges absolutely for any of the x's between x minus a is less than some radius of convergence. Great. It's all good and well. But where is the theorem? What does it say? What's cool about it? It says that if I want to know what the derivative of this function is, then I can take the derivative of the power series term by term. And this is not a trivial statement because this thing is infinite. Okay, so what I'm about to write down, it may seem obvious, but it's not obvious for something that's infinite. Okay, so anytime we have infinity, we have to be careful. But it does end up being true that we can do this. So think about taking the derivative of this guy. What are we going to do? We're going to bring down the exponent. And then we're going to subtract 1 from it. So the derivative of the function, which is what our power series converges to, is equivalent to the derivative of the power series. Which, like I said, seems obvious, but is non-trivial because we're looking at an infinite sum here. Not trivial. And indeed, this is still absolutely convergent for the same radius. So we can take the derivative of a power series and we get yet another power series that is also absolutely convergent on the same interval. But it gets better because I can take as many derivatives as I want. So take another derivative. Yet again, we bring down the power. And then subtract 1. Actually, there's one point that I failed to make. It's relatively important, but not a huge deal if you slip up on this. But when I write down my derivative or its second derivative or whatever derivative, the index that the sum starts at changes. And it's really a matter of what do I want to say? Simplicity. I could have wrote n equals 0 here, but because I've got an n term in the series, if I plug in 0 for that, it kills that term. So I'm not getting anything by starting my sum at 0. The first non-trivial term is at 1. So when we write this down, we start the series at 1 for the first derivative. For the second derivative, we start it at 2. For the same reason. If I plug in 0, it kills the term. If I plug in 1, it also kills the term. So only the first non-trivial term is at 2. And so we can take as many derivatives as we want. And in fact, I could write down an equation for the kth derivative. So I can take k many derivatives, assuming the function has that many derivatives. Then we have a sum that starts at k, goes to infinity. And the term that we would have here would be n factorial over k factorial Cn x minus a to the n minus k. So I can take as many derivatives as I want, assuming the function has all those derivatives. And it tracks as far as how it affects the power series. So this can be useful. Sometimes we want to know things about derivatives. So suppose we're looking at the function 1 over 1 minus x. We know that this is the limit function for the geometric power series, x to the n. And here I won't be quite so loosey-goosey with my bounds, so I'll go ahead and put them in just so it's clear. If I want to know the first derivative of this guy, instead of computing the derivative here, which requires a chain rule or whatever, I can just do the derivative of the power series. That one will start at 1, go to infinity. We'll have an x in x to the n minus 1. So like I said, power series are really useful tools for approximating functions. When we're doing stuff with computers, we can't actually perform infinite sums. It would take infinitely long to do so, but we can perform really large sums. So I could take this series and compute it up to, I don't know, 2000. And that would be a really good approximation for the first derivative of this function. Why would you do that? There may be good reasons to do that. Here, it doesn't make much sense since we can find an analytical derivative, meaning I know how to take the derivative of this function. But some functions we don't know their derivatives, or the derivatives are really ugly or whatever. Right. So if we can do it with derivatives, then we should suspect that we can do this with integration as well. Think of the second fundamental theorem of calculus. We know there's this intimate connection between derivatives and integrals. So we have another theorem. This one just connects power series to integration. So suppose we have a convergent power series centered at A. We know that it's absolutely convergent for any x minus a's less than the radius of convergence. Then what does the theorem say? It says then the integral of our function f of x dx is just the integral of the power series. So we do this term by term. What do we do with integration? We add 1 to the power and then divide by the power. And here with integration, we don't have the same issue with the index of the integral. So we can still start our sum at 0. So we can integrate power series, we can take derivatives of power series. They're pretty versatile critters. We can do a lot with them. And so let's look at one nice example that shows you the power of these techniques, how we can use them to compute things. All right, so here's our power series. We've got an alternating component. We've got x to the 2n plus 1 all over 2n plus 1. And we're starting at 0. Okay. So that's a power series. And assuming that we're within the radius of convergence, we know that it's going to converge to some function. The problem is for us to find the function. So how to do that? Well, let's start by taking a derivative. So we don't know who f is, but we know it's power series representation. So we can take a derivative. And if we do that, we're going to get we're gonna drop that 2n plus 1 down. It's gonna cancel out with this 2n plus 1, and we'll just end up with the alternating component times x to the 2n. And this is starting at 1, going to infinity. And look, this looks like a alternating geometric. Um, it's an alternating geometric, and here it actually does make a difference where we start the sum. So remember what I said when I was presenting the theorem to you. I was saying, you know, we start the sum at 1 because it doesn't make any difference. But here it does make a difference. So we only change the index for succinctness sake. Here we don't change it because we'd actually be losing one of the terms in the series. So it's not always necessary to change the index, only when it would make no difference. But here it makes a difference, so we keep the index starting at 0. All right. So we have a geometric. Actually, I should write it slightly differently. So just to make it clear, how does this thing actually look? It looks like negative x squared to the n. There we go. So now you can see that we have a geometric series. So we know what this thing converges to. 1/1 minus the radius, the ratio. So that gives us 1/1 plus x squared. And of course, we need to always bear in mind what the radius of convergence is, at least for absolute convergence. So for absolute convergence of the geometric series, we need the absolute value of x squared to be less than 1, which is the same as the absolute value of x being less than 1. So we have absolute convergence within that radius. Okay, very good. But we don't actually know what the function is. We know what its derivative is, which is useful, of course. But we need to get back to the function. So what did we do? We started with just a power series for some unknown function. We took its derivative. We found out that that was a convergent, an absolutely convergent geometric power series, whose convergent function we knew, right? We know how geometric series behave, but that's not the function we want, right? That's the derivative of the function. So how do we get back to the function? We take the integral. So let's find f of x. F of x should be equal to the integral of this guy dx. All right. It may have been a second since you thought about integrals, since we've been doing so many sequences in series, but this is one that you probably know fairly well. So if you don't know, then you should know how to get it, right? We can use a trigonometric substitution here to get the actual integral, but we don't need to do that here because we know what it is. It's the inverse tangent of x. But this is an indefinite integral, so that means we have a plus c here. So what do I do? Well, I know I have to figure out who this C is in order to completely define the function. Right now, this is really a family of functions, each one differing by a value of C. But I know who the original function is. It's this power series right here. So I can use that power series to help me figure out who C is. Because the function here should agree with the function here. So we're going to plug in a value. Might as well be 0. Usually makes things easier. And we're going to plug it into the power series. So we're just plugging in for x. And when we plug in 0 for x here, it kills everything. So what do we get? We get 0. So that means that when I plug in 0 into my function here, I should get the same result. So now let's plug in 0 into this guy. And what do I know? I know this must, it's an exclamation mark, this must equal 0. So this is going to help me figure out who C is. The inverse tangent of 0 is just 0. So since this must equal 0, that implies that C equals 0. Therefore, the function is just the inverse tangent. So there you get to see the power of these techniques. If you just know a series, you might be able to figure out the actual function. You may ask yourself, when will it ever be the case that you only know the series of a function, you don't know the actual function? And I keep on bringing up this example. You don't really have the context for it yet, but when you get into your ordinary differential equations class, you're going to be learning how to solve differential equations. And there's a lot of differential equations whose solution we can't find directly, but we can use a power series to find a solution. So we'll get a solution from a differential equation that is a power series, and we may be able to translate that power series into an analytical function. So we may end up in a situation where we get this as a solution to a differential equation, and then we can use techniques like these to actually figure out who the series is as a function. So pretty cool stuff. What we'll be talking about next time, unless I'm mistaken, is we're going to start talking about Taylor series and Maclaurin series, which are ways of taking a function and rewriting it as a series. So really powerful and useful stuff. Probably in terms of the utility, Maclaurin and Taylor series are the most useful thing that you'll learn in this class. In terms of general applications in mathematics research or science research, chemistry, physics, biology, whatever, any one of those fields, you may have to solve differential equations, and using power series to do so is very common. And the Maclaurin and Taylor series are also useful tools. So we'll be talking about that next time.